When it comes to pressure testing, we've already talked a little bit about the fact that there's not like one number that you can rely on, but I will tell you what we do, okay? And this is for standard split system installations, service calls, that kind of stuff. The first thing to know that's kind of weird that you may not know, what is the weakest part in the entire system in terms of likelihood of being damaged by overpressure? I said that really weird. What is the part of the system? Say it again? Blower motor. On airflow side. I'm talking about with the refrigerant side, pressurizing the system with nitrogen. What is the system that's most likely, part of the system most likely to be damaged by getting too much pressure? Service ports, coil. We're just going theories right now. Theories. What's that? Distribution tube after TXV, that's a good one. All good ones. But the weakest part of the system is actually the compressor terminals. Okay? Now, what sounds wrong about that? Because I guarantee it sounds wrong. Why does that sound wrong? Because it's highest pressure, right? Compressor is the highest pressure point, not the shell. The shell of the compressor is the lowest pressure point in the entire system. Gas, most guys don't know this. Refrigerant gas goes in down the suction line, and it just drops into the compressor. It doesn't go right into a compression chamber. It just drops into the shell because it's a refrigerant-cooled compressor. It's cooled with refrigerant vapor, right? So you have the windings, everything is all immersed in there, and you have your terminals. Those terminals are metal, and they go through glass, fusite. You guys have all seen compressor terminal venting before, right? Where a terminal blows out of a compressor. That actually is all on the low side of the system, and that is the weakest part. And that's why you got to be really careful when you're taking plugs on and off of compressors. You see a lot of guys do a lot of this on them, and overpressure, all that. So when you're pressurizing a system, you need to look at the inside and outside system and look at the maximum pressurization and never exceed that. Okay, and a lot of times the max pressure of the condenser is actually a lower max pressure than the fan coil, air handler, whatever. Because a coil, it's just metal. Like there's not a whole lot going on. You could have, like you said, you could have the tube on the expansion valve or the expansion valve itself or whatever. But the actual weakest point, most likely to fail, are those compressor terminals. So when you pressurize a system, you pick a number that's below that. For us, typically speaking, we're also picking a number that's below the external equalization shutoff of the expansion valve. Okay, we're going to talk more about this later, but I want to tell you something you've probably all seen before. When you're pressurizing a system with nitrogen, where do you put the pressure? How do you add pressure to a system when you're nitro pressurizing it? What's that? So yes, where? Where do you let the so you use a regulator on a nitrogen tank, you hook it up. Where do you put it in at? Liquid line. Somebody said that. Somebody said suction line. Liquid line from both ends. All right, we got everything's covered here. We've got all gender preferences going on here at this point. So most people put it in the liquid line, okay? And what happens? You watch the pressure go up, they both go up, right? So you put the pressure in the liquid line, it goes up, suction goes up with it, right? And then what happens all of a sudden? It just stops. Why? The valve slams shut, right? So this is the basics of a valve, how it works. We'll talk more about this. This is the one part of the magic of the industry, right? You have these pressure balances in between the system. And that external equalizer tube that connects to the end of the evaporator, it has nothing to do with equalizing pressure when the system shuts off or anything like that. All that tube does is it acts like the pressure sensing device. It acts like when you're measuring superheat or subcool, you measure a pressure and you measure a temperature, right? Well, imagine that's what that valve is doing. It's measuring superheat. And it's measuring the temperature with the bulb, and it's measuring the pressure with the external equalizer. And that is the closing force of the valve, meaning the pressure on that external equalizer is what closes the valve. Once the pressure gets to a certain point, it is completely shut, and now it doesn't allow any more refrigerant to come through. That's when you hear that term hard shutoff, or non-bleed valve, non-bleed TXV, or hard shutoff TXV. That's what they're talking about. So typically, when we're doing it, and again, this is for a typical system, we're only going up to just below that point where that occurs. So 120, 130 PSI, something like that, and then we're letting it sit for an hour or so. But we also did a visual inspection on everything, and we did a bubble test inspection, and we're measuring it with digital devices to show any sort of drop we're going to be concerned about as long as there's not a temperature change, right? Now, when you get to big, complicated systems, VRF systems, VRV systems, refrigeration systems, long line sets with lots of connections, then that's when you do higher pressure and you let it sit longer, okay? A lot of people would call it heresy, what I'm even telling you right now about how we do it, but it's the truth. It's what we do. Even if we go to 120 PSI, something like that, we're ending there. If you guys do higher than that, great. If you do longer than that, excellent, right? That's awesome. But we do that just so that way, once we set it, we know it's set. When you go in from both sides, you can do that. But the downside is they may be slightly different from each other, right? And then that can potentially confuse you. You go back and you miss it. Is that a big deal? Not necessarily, but if you do exceed the pressure, now again, you have higher pressure on one side than the other, that's a non-bleed valve, but it could bleed a little bit, right? And then that gives you the false sense that you have a leak when you don't have one. So that's why we stay below that point where it actually traps it. Not really doing the best job of explaining this, but all that is to say, set it at a fixed pressure, put it into, if you have digital gauge set or field piece probes or whatever you have, put it into that delta P, which means chain. Delta just means difference. Delta P, difference in pressure. Put it in that difference of pressure mode and just watch to see if it drops over the period of time. And like you said, temperature compensating is really good if you're going to be there for any amount of time. Like if you're going to be holding it for a while, that's a really good thing. Bubble test every joint, look for that foam, and then when you get to vacuum, now you're also making sure that you hold a decay test. So it's that multi-pronged approach. Visual, pressure test, bubble test, vacuum decay test. Tells you whether or not you have leaks or not. If you get into cases where you're really chasing a hard to find leak, that's where some people will say, use a leak detector, put some refrigerant in it, all that kind of stuff. I almost never find that we need to do that when we're doing installs, because right now we're still talking more about installation practices. That's really not that effective, honestly. In service, obviously, the electronic leak detector and bubbles are the way to go. That's obviously what we're using in most cases.
One thing, never release the pressure before putting vacuum.
Never release the pressure?
Release the pressure off.
Before you put the vacuum on, yes. I have certainly created, yeah, the volcano of oil that comes out of the top of your vacuum pump is not very unpleasant.
What are your views on dye? Like, for example, different methods?
I don't like dye because I don't like it getting all over my tools. So it's very messy. But there are cases where UV dye makes sense. Again, we use it. We've used it in some cases in big refrigeration systems where you're going to come back often. And you're going to be there a lot. They use it a lot in cars because in cars, there's so much there. There's so much in the way that just the ability to kind of see it sometimes is helpful. But then the problem is, once you do find the leak and fix it, now you got to get all that cleaned off now too. Otherwise, it's going to be a false positive. So I don't love it. A lot of people will say, well, you don't put that in there. You only put oil and refrigerant. The compressor manufacturers don't like it. And of course, it's true. They don't like it. The main reason they don't like it is when they get warranties back and they have to cut it open on their bench and it gets all over them and it makes a giant mess and pisses them off. So they say, I don't want this anymore, right? I mean, be practical. Do I really think it's hurting the system? Probably not in most cases. They wouldn't want those lawsuits, Spectraline and all those companies, but I really don't love it. My take on dyes would be last resort, complicated systems, especially stationary systems where you're going to be going back a lot, like maybe big food service applications, grocery stores, that kind of stuff. And residential, I just don't think you need it. Have a good electronic leak detector that you know how to use and you know how to maintain. I'll tell you, and again, I'm going into the service side of this conversation quickly. Nothing drives me more crazy than when people say, I don't think my leak detector's working. Either it is or it isn't. Don't think that it's not working. You can know whether it is or isn't working. And a lot of times it's because they just don't have a good leak reference. And that's one of the reasons why I love the H10 Pro, is that it's got that leak reference right there that you can utilize that kind of gives you that indication. It can be a little tricky with some of the others, but again, even if you just give yourself, you just go to the tank and just kind of, and then let it kind of vent out a little bit so it's not that intense and then bring it to it. It should be going off like crazy when you get close to that. Go ahead.
I wanted to say that most of the times when we doing the leak testing, we usually concentrate on the joints that we make, on the connections that we make. But it's also important to note that the shutter valves and the service valve are also another points to leak temperatures.
Yeah, and that's actually one of a really good best practice when you're walking up to a system that you know has a leak or you know is low or you even suspect it. If you know you're already going to need to do that, bubble testing the caps before you even pull them off. Especially if you see oil. So if you already are seeing oil and so you suspect, because nothing's worse. And again, this is senior techs have had to deal with this for a long time, where the other guy, I replaced, cap was off, straighter leaking, put the cap on, it works, it's working fine. It's the recharge. It's like, no, come on. Was it really the cap? Was it really the straighter? Or are you just using that as an excuse to get out of the job? And you know how often that is the case, where they'll use something dumb and it's not that dumb thing. And so just going up before you even pull those caps off, just quick dab it and just see, do I actually have bubbles or not? Because if you don't, and you've done it right, then don't focus there, right? Focus elsewhere. But to your point, yes, it isn't always just the connections that you've made. We're even running into cases now, and I don't know if you're seeing this, where you have line sets that are reacting with the copper, and you're actually getting corrosion actually within the line set on some of the ductless systems, especially with the white foam tube insulation. Have you guys run into this at all? I mean, we have, and there are certain types of Chinese line sets that are actually corroding in the line set itself. And so you always have to be open to new things that are causing it. One real common one that we'll run into is water softening equipment, where they use salt as the regenerator, and the salt discharge goes onto the copper line set or drains near it, and then that causes corrosion. Or sometimes it's the condensate drain is dripping on the copper, and the client likes to use bleach in their condensate drain. Just using your senses first before you start going crazy with tools. Tools are important, but use your senses first. Use common sense. Where's the most likely places for this to leak? And kind of eliminating those before you move on. And that goes down to just don't always pull the caps off. If you see oil around those caps, don't just pull them off. You want to confirm whether it's leaking before you even pull them off. Because once you pull them off, now if you put bubbles, you're going to get bubbles in the port, and it's just it's a whole thing. So, which is also even simple things. Like when I pull caps off, the first thing I do, pull the cap off, I look for the seal. I just automatically look at the seal every time. Every time I use a multimeter, before I even start using it, I put it in an ohm scale and go dee, 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 then I use it, right? You develop habits so that you prevent those stupid mistakes where it's like, oh, I'm not measuring voltage. Shock yourself, because it's just your probe isn't connected properly. It's just something stupid like that.
Don't use the cover from the refrigerant tank.
Do not use the refrigerant tank cover. Good point. Caps on the tanks, a lot of times actually sometimes they don't have seals, and sometimes they go down too far and will actually depress the Schrader. They'll actually go down too deep. You're doing a leak detection on an existing system, and maybe you've been there once or twice. Slow down, right? Electronic leak detection is not a fast game. It is just slow the process down. Even when you do the whole, I'm sure it's the evaporator coil. It's the evaporator coil, great, move away. Like, no. Slow down. Confirm that that's the only leak you can find. Look for oil. Pay attention. Don't get sloppy. Because there's nothing worse. Again, you guys have all probably been through this. Oh yeah, we swapped the evaporator coil. And then a month later, it's low again. It doesn't matter, even if that evaporator coil was leaking, and even if you can prove it, that client is mad as a hornet, right? And it doesn't matter if it's your fault or not. If you can prevent that problem from happening by being a little bit more thorough, just slow down on leak detection. It's a really, really important thing. And again, I've learned that the hard way.
The big problem for us is line sets. It's hard, obviously, you can't confirm a line set's leaking unless you have, unless you do a full pressure test, isolation test, right? So that's a lot of work.
It is, yeah.
We used to have two different categories for leak search, either electronic and visual, or an isolation. Isolation was a lot of money.
Right.
Not a lot of people wanted to spend $1,000 on an isolation test.
Right.
So we put them together, did it a little bit more than electronic, and we find the leak no matter what. But the problem with that is that little bit of money isn't a lot to spend, whatever hours it takes, 6 hours, whatever, if it's a small leak, to actually confirm there's a leak in line set. It happens so it's not very frequent.
Right.
So for us, at one point, the old service manager wanted us to be pressure testing every single
right.
system, right? Which it gets hard if you got multiple leaks.
Right.
So it's one thing if you can't find it in your evaporator, you can't find it in the condenser. Okay, now we
Correct. Correct.
Right? But so that's tricky. Like I thought the right solution was do a smaller price for electronic, and then hey, if you want us to confirm that everything is sealed 100%, we have to do this procedure. But I advise people, hey, look, if it is something else, we'll come back for free. We'll do the research because you would have needed to pay for this anyway.
Correct. Just the difference, right? So then you just charge them the difference between the two. But either way, if you can, and that's where that's where when you slow down with leak detection, one of my favorite things to do is to make the client see that you have an electronic leak detector and it's going off, if at all possible. If you can't, you can even video it. Like, look, here's the thing. Like, I'm doing the test. It's showing that it's leaking. False positives used to be a lot more common than they are now, depending on the quality of leak detector that you have. So if it's going off in the evaporator and you can keep going to that same point and it keeps going off and it clears and it goes off, and I always do it at least 2 or 3 times. Goes off, clear it, goes up at the same spot, clear it, goes up at the same spot. Okay, I've got a leak here, at least somewhere in this vicinity. Now the client can decide, do I want to do more? Do I want to go further? Or do I just want to do this? If we put this in and there's other leaks, I'm just going to charge you the difference between the electronic and the nitro pressure test. That is, when I say that's how we do it, okay? That is how I do it. I cannot, there are 2 layers of leadership between me and my residential service manager now. So does that happen every time? Maybe not, but that is what has been communicated to be done, yeah. It's tricky, because that's really up to the tech, right? The tech has to be the one to have that conversation. And when you get busy, you get in a hurry, but it does pay dividends when you can slow that process down a little bit and say, hey, just want to talk through how leaks work in an air conditioning system. Your system's low on refrigerant. It should not be. Refrigerant does not need to be added. It's not like oil, change your oil, that kind of thing, right? If we don't have enough of it, it means we have a leak. I found one leak in a very common place for them to leak. I looked at some other common places. I'm not seeing anything. But that doesn't mean that I can assure you there are no other leaks. That's a pretty quick conversation, and that will help a lot of those problems. But it's a challenge, right? It's a tricky one. Go ahead.
Regarding refrigerant leaving the unit, each time we go for a gauge, refrigerant come on, right?
Yeah.
So what happens if we keep on looking at refrigerant and then there's a
You make a good point, but again, that's also part of where I would tell you to adjust your process based on the type of system you're working on, right? So if you're working on a split system, a typical split system, unless you get a liquid line Schrader that sticks on you, you're not going to lose that much refrigerant. Now again, that's also where using probes is really helpful too, and using core depressors. Those are really nice ways to help prevent that problem. Or if you know, old school guys used to use lollipops, it's just the gauge and it's the port on it, right? You just literally connect that. Even in market refrigeration, they still do that a lot. Like, I like them. I mean, I do. They're not that accurate. I feel like I said something I wasn't supposed to say there. So part of it is the tools you use. Part of it is being really careful with the liquid line. Like I said, core depressors can help with that. I don't like it when people use that as an excuse, like, well, hey, your system's probably low just because we connected and disconnected so many times. It's like, I mean, how many times have you really seen that? Now, on a ductless system, yes, maybe. But that's also where, don't connect to ductless systems. What are you going to get out of that information anyway? It doesn't tell you anything, right? So just start using line temperature, use the air discharge temperature. If you want to be real fancy, do a delivered capacity test with some psychrometers. You'll get some clients to be like, well, the last guy connected. And you say, the reason why we don't do that and we use more advanced tests is because we don't want you losing refrigerant. And there's a very rare client who's going to, bug out about that.
The guys that go around connecting to every system is post the data onto the customer's file. So you can see, every time someone hooks up, you know what the pressure is.
Right.
So if you're way different than that, you know that it wasn't anybody connected.
Right.
You always know what it was when you checked it. You never have to question someone else. So
yeah, that's a really good point. And again, I'm not saying that you're not wrong. You're right. But a lot of it comes down to some old practices where people every maintenance, every 6 months, big old 6-foot hoses and gauges that look like the size of your head that hold 2 pounds of refrigerant,
At the end of the year, you probably see them.
You might in some cases, right? And that's where I would just suggest not, yeah. So is it possible? Sure, but yeah. Good.
I don't trust the electronic leak detector because I had a little yeah, I wouldn't say accident, but I was checking for a leak and it went off, but someone sprayed some bubble test.
Okay.
In their leak bubble, and it went off.
Yeah.
And the installer took down the air handler. I said, where's the leak? He said the leak detector went off. So from there it does like anything different.
It does, yeah, it does. But again, here's another thing, and this comes down to basic psychology, okay? We are all wired, so this isn't going to be a long psychological speech, okay? It's going to be short. But we are all wired to be avoidant for our worst mistakes. Our worst mistakes begin to define us, right? And the reality is, you might do that 10,000 times, and that might have been the 1 in 10,000 because you've done this a long time. Don't let that take an electronic leak detector and throw it out the window because, like, again, and keep this in mind, we work on grocery stores that have thousands of pounds of refrigerant, where leaks cost millions of dollars for these clients. And we use electronic leak detectors all the time with great success. It's just that, yeah, sometimes somebody uses, like, for example, Big Blue with a good quality leak detector is not going to go off. It is not going to go off. But some people could use some weird bubbles or something, and it might react to some sort of molecule that's in there. And just being as rigorous as you can be. And that's what I typically do is I try to find the spot. So if I can find the spot on the coil, I'm looking for oil, I'm looking for any indication of something going on. But there's been coils where I've pulled the fins all off to get to the spot, and it's just like this little pockmark, and it's like, why? I did a video on a Mitsubishi ductless where I did that, where I literally ripped the coils down all the way down, and it's like, there's just this little tiny spot on this coil, and I have no idea why it's leaking. I would just encourage you, electronic leak detectors, good ones. H10 Pros, Stratus, a couple others. We use them all the time, and we have really good luck with them. To your point, you are going to have that outlier where you're going to be wrong. But again, this is where your motivation is to do right by the client. Like, you're trying to do right by the client. And if you're proven that you didn't do right by the client, then I'm sure you work for people who they're going to understand that, right? Like, I did everything I was supposed to do, and I was wrong, and that happens, right? Doctors, happens to them all the time. So I wouldn't get too hung up on that. To your point, though, to eliminate all possibility, yeah, line isolation test. Isolation test is the way to do it. It's just expensive, it's time consuming, who wants to pay for that? You know, it's this trade-off that you have to do.
Confirm.
Yeah, as much as possible. Yeah, confirm. Wherever possible, confirm. But again, look at the brand. And again, this is something I would encourage you. I don't know what brand soap bubbles you're using, but test that, right? If you're using a brand that's not Big Blue, that's okay, but just test it and see, are your leak detectors going to react to that? And that's the thing I always say. When it comes to leak detectors, number one thing with leak detectors and vacuum pumps is you have to maintain them. You have to test them regularly. You can't just expect that they're going to keep working. A lot of them, in fact, all heated diode leak detectors, that heated diode has to be replaced periodically. And if that thing's 5 years old, it's probably barely working anymore. So you have to kind of keep up on that and know your tool really well, know how to maintain it.
Calibrate.
Go ahead. Yeah, calibrate it too, yeah.
Of course. You use electronic leak detector, right?
Yep.
Search for a leak.
Yep.
And you pressurize the system with nitrogen.
No. No. Nitrogen, and again, so remember, the air around us is mostly nitrogen. So how would that work, right? I mean, like, a leak detector would be going off like crazy because the air is mostly nitrogen around us. There is a way you can do a leak detection on a system with only nitrogen, but that's an ultrasonic leak detector. Ultrasonic listens for the leak. And for those of you who are a little gun shy about old school leak detectors, you really don't like them, I would encourage you to try ultrasonic. It's like a Ford Chevy conversation. It's like some people like, oh, that was a bad example, DeWalt Milwaukee situation. Some people like DeWalt, some people like Milwaukee. I don't like ultrasonic. I could never get used to it. Craig Miglaccio, AC Service Tech on YouTube, one of the best techs I know, one of the smartest guys. He absolutely loves ultrasonic. Uses it all the time for everything. So you know, you can try it, and it does work. It just actually hears that sonic sound of the small orifice leaks.
You can use the 410, I think 410.
Yeah. Yeah, and that's what you do. You put a little bit of refrigerant as a trace gas, a little bit of 410 and that. But again, the more diluted it is, it's not going to pick up as well, right? So the less 410 you use, the harder it's going to be to find. And so it is a little bit of a trade-off there. Again, if you're at the point where the system has no refrigerant in it, then electronic leak detection, usually I don't need it, right? Like, you've already almost won there. If it's got no refrigerant in it, it's usually not that hard to find. It's the ones that are like a couple pounds every couple months. You know, those are the ones that kill you. If you walk up and it's flat, and it was like, oh yeah, it was flat a week ago and now it's flat now, you find that leak. That's what we call a hisser. Put a little pressure in there, you'll usually hear it. So, go ahead, Matt.
I have 2 leak detectors. I have a heated diode and then the
ultrasonic, infrared. Infrared.
And so I like having 2 because I can confirm they don't catch the same kinds of leaks, or they're good for different sizes. But yeah, I like to just be.
Matt goes in with one in each hand. He's just like, just doing it that way.
Yeah, I'm carrying both. And,
yeah.
And
it's not a bad idea, honestly.
The diode is great. Like if there's a leak, you'll walk in the front. At least mine, I walk in the front door and it goes off a lot of times. Yeah, the Philippines one. I mean, it's great. I mean, it's like by the time you get to the attic, it's pretty much useless.
Yeah.
Because it's just going off everywhere. But yeah, like. Yeah, I like to have 2 just to
yeah.
give it a good.
And that's what I like about the Stratus, which is the most expensive leak detector on the market and the best one. It's an infrared, but it also is a self-zeroing infrared, so it's constantly zeroing, and it actually gives you a parts per million readout. So you can literally walk in the house and be like 1, 2 parts per million, 3, 4. You know, like we do it in grocery stores all the time, where you walk, like you just start like, oh, okay, I think the leak's over here, you know, and you just get closer and closer. So it's like most things. You get what you pay for. It's different qualities. It depends on what tool you have. But again, biggest advice I would give you is be patient and know your tool. Meaning that if you have not read the maintenance and care manual and calibration manual on your leak detector, then do that. It won't take that long, and then you'll know what to do. And if you don't know like where to get the sensors or where to get whatever, well then find out. TrueTech Tools can probably tell you pretty easily where to get them from. Because you do need to do regular maintenance. Most of the times when I see people who have terrible success with electronic, it's because their electronic isn't working great. Or they're not being patient, or like in your case, you've had some bad experiences, because there are. I mean, you're going to have them where you feel like you've done everything you can do and you still don't get it. And you just got to be okay with that sometimes. None of us are going to be perfect.
Yeah, like I don't trust my heated diode that much because it goes off. I mean, if you walk too fast with it, it goes off. Like
if you jar it, yeah, sometimes.
Yeah.
If you block the sensor, yeah, it'll
just go off all the time. But so you kind of just have to know the limitations of each one, and then the other one is like it only goes off if there's a leak, and it's got to be a pretty decent size leak. So.
Which is where ranging it properly and all that is key too. Yeah.
Yeah, so it does take a while. You know, you get more confident the more you understand how your tool works.
Yeah. And that's why you get people who are super loyal to each one, because it's not that it's better, it's that they're just more used to it. They followed it. And those 3, heated diode, infrared, and ultrasonic, all have very specific ways you have to use them. Like heated diode, they're useless until the diode warms up. So you have to let the thing heat up before you even start to use it. And then you got to range it in and all that. Whereas in infrared, you have to move it all the time. Otherwise, once it hits, it'll stop going off on you, and you got to move it again. You know, so they all have their things, which might be a fun thing to do. Actually, a fun thing to do might be to get some of you to bring some of your tools in here and like do a little roast on what we've got. I'm sure you would love that. That would be fun. So this just covers basically just the difference in pressure. Anytime you're going to let it sit for a long period of time, and temperature clamps, kind of getting an average across the system. Looking at that average change, and then calculating it. That's really the right way to do it. And again, that becomes more of a factor the longer you do the pressure test. And it never hurts to do a pressure test longer, right? If it's really critical, it's a multi-zone ductless, for example. You got multiple heads running all through, and you don't want to leave before you know, then let it sit overnight. Let it sit a couple days. If you're doing, like I said, a VRF, VRV system, a couple days at 600 PSI they'll do. Grocery stores will do them for really long periods of time because, like I mentioned before, the more the internal volume, the longer it takes for it to show up on a gauge when there is a leak. The smaller it is, the quicker it shows up. That make sense? Smaller, quicker? Okay, got it. We'll do some quick evacuation stuff. I want to specifically address, and I'm not going to have much in the way of slides to address this. You guys have probably, a lot of you have probably seen my video on evacuation and all that. That's a big one that's come up. But I just want to start with, we'll just talk more about the basic science of evacuation, like just the basics here. So, why do we measure vacuum in microns versus PSI?
Very small pressure measurement.
It's a very small pressure measurement. And the way that I usually, because a lot of guys will say, well, look, you know, you had the old gauges. I just let the gauge peg on the suction side. I listen for it to make sure it starts to sound nice. I do smoke a couple cigarettes, or here maybe left-handed cigarettes. I don't know, something. And if we're good, flame joints. Flame joints. Okay, yeah. And that's how you pull the vacuum, right? Well, what's wrong with that? Well, the goal is, what is the goal? The goal is to get almost all of the stuff out of inside the system, right? Can you do that? That's the question. We're going to talk about that in a second. Get almost all the stuff out of the system. Okay, in order to know that we get almost all the stuff, we have to measure it down to a very small amount. Now, people who say, why do I have to use microns? I use the example and say, okay, I want you to measure off 5 feet for me. So you'd be like, hand me a tape measure, right? I'd be like, no, here's the trick. You got to use the odometer on your car. The odometer on your car to measure off 5 feet. Could you do it? Well, an odometer measures distance, right? So why wouldn't that work? Well, because it doesn't measure a small enough distance. And that's actually all a micron is. A micron is actually a measurement of distance. It's actually a millionth of a meter of mercury column. That's what it is. It's a tiny, it's the pressure that it takes to move a mercury column 1/millionth of a meter. Tiny measurement. So that's why we use a micron gauge. And that's why a micron gauge doesn't really work for anything else. It's only for one purpose. The other thing that's interesting about a micron gauge, you'll notice that you never zero out a micron gauge. Anybody here ever used a micron gauge? Let's start with that. Who here has ever used a micron gauge in their entire career? Let's start with that. How many people presently use micron gauges? Okay, a little bit less. All right, good. Okay, fair enough. Good, so you at least use them. You don't zero them. Have you ever noticed that? Because a micron gauge is in reference to no pressure whatsoever. That's what it's in reference to. So it doesn't matter. Zeroing is all about differentials in pressure. Zeroing to atmospheric pressure. With a micron gauge, you're trying to get it to nothing. Which brings us to our next kind of concept. There is no such thing as negative pressure. I'm going to pause there. There is no such thing as negative pressure. There is only pressure that's less than the pressure that we're used to. And here, because pressure is 14.7 psia at atmospheric pressure. Right now, we are at sea level. So we are at sea level. We are at sea level, so that means we're right about 14.7. Okay? When we say something is a vacuum, all we mean is that it's less pressure than what we've got. Right? That's all. We're already sitting at the bottom of an ocean of air. Right? So there's an ocean of air above us, or all around us, and we're at the bottom of it. 14.7. If we go up higher in the ocean, would we say that that's negative pressure? No, we just say it's less pressure. Right? That's all. And when you get to the surface, now there's no pressure. That's zero pressure. That's what we're, in terms of water, in this dumb metaphor I'm giving you right now. But what we're trying to do is get to nothing. No pressure. We're not getting to negative pressure. So when we get to negative 14.7 psia, that is equivalent to 0 microns. Now, can you get to 0 microns? No, you can't get to 0 microns. You can't get there. We can get pretty close. We pulled systems down to 15, 20 in some cases, which is a really, really low vacuum.
How long does that take?
What's that?
How long does that take?
Well, it depends on the size of the system. So if it's like a ductless system, I mean, you can pull a system down to 20 in some cases in an hour or something like that. You can pull systems down. I mean, like we pull, our standard vacuum is 200 microns on a split system. So a 4-ton system, 200 microns, and our average vacuum time is about 20 minutes.
Is that new install or?
New install. New install. About 20 minutes, 200 microns, that's typical. And it's not a problem. It's not like hard. It's not challenging for anyone. It's just what we do. So what are we doing when we do that? We're getting all the stuff out. Now, here's a quick thing. What stuff do we get out? Does a vacuum pump pull dirt out of the system? No. Does the vacuum pump pull liquid water out of the system? Trick question. If it has to evaporate it first, right? So it boils it, and then it pulls it out of the system, right? So when people say something like, do you guys ever say the word or hear the word non-condensables? Do you ever hear that word? People say, oh, it's got non-condensables in the system. What are some examples of non-condensables? Moisture, oxygen, air. Well, moisture is an interesting one. A lot of people will say dirt, right? Think about the word non-condensable. It means it cannot condense. Can moisture condense? Yeah, it sure does. I mean, otherwise our ocean wouldn't be full right outside here, right? So what is a non-condensable? Non-condensable is a gas that does not condense. So that would be nitrogen, oxygen, air. That's basically it.
So I guess anything that kind of change state through the refrigeration.
Correct. Anything that's not going to change state in the normal conditions of the refrigerant cycle, right? That's what it is. Non-condensables, when they're left in a system, they tend to get stuck on the top of the condenser. They take up condenser space. They drive up head pressure. Obviously, if it's oxygen, that can create reactions that we don't want. So non-condensables are a problem. A vacuum pulls out non-condensables. That's what it does. That's what it's for. It can't pull out dirt. It has to boil liquid water before it can pull it out as water vapor. But this is one of my pet peeves when people say, oh, I think the system has non-condensables in it. I'm like, what makes you say that? Well, it has a restriction. That's not non-condensables. That's dirt, cupric oxide, piece of solder, something like that. Liquid water, whatever, ice. Could be lots of things inside the system, but that's not a non-condensable. Vacuum pumps do non-condensables, and they do water vapor. So, but in order for it to get the water vapor out, it has to first change it from liquid water to vapor. Go ahead.
Can vacuuming a system freeze the water?
There you go. Can a vacuum freeze the water in a system? And the answer is yes. The real answer is, the scientific answer is yes. The real answer for all of you is no. You will not be able to do it. So if you take a system with copper lines and copper coils and everything else, you will not be able to freeze water with a vacuum pump in that system. If you do it in a glass container and you take a vacuum pump and you hook it directly to a glass vessel with water in it and the ambient temperatures are low, you can do it. There's videos of it being done. My friend Neil Comparetto did it. It has not been effectively done in any real system that we work on. If you work on a freezer, yeah, for sure. In fact, in a freezer, if you have water in the system and it gets into the evaporator coil, it's going to freeze just because of the temperature of the evaporator coil. If you live in Detroit, Michigan, and it's -20 outside, yeah, you better believe any liquid water in that system is going to be frozen, right? Can you freeze it with a vacuum pump? The answer is yes. Can you do it? No. Because as you try to do that, more heat energy is going to keep entering from the copper, from the coil, from everything else, and it's going to prevent that from actually freezing. This is one of the things where theoretical scientific knowledge actually gotten in the way of what a lot of people's practices were. So what would happen is guys would hook up with big hoses and a big pump, and they would say, no, you can't do that. Don't pull the vacuum fast enough, because if you pull it too fast, you're going to freeze the water in the system. And it made sense, because sometimes you'd get in it, it would stall on you, you'd have these issues. But those are all caused by other problems, not ice in the system. It can appear like that's what's happening. If you do it right, freezing water in the system will not be a problem, and you will pull vacuums in under 20 minutes on new equipment. On old equipment, it's still a challenge, because on old equipment, moisture, refrigerant, everything else gets entrained in the oil. And once it's in the oil, getting it out of the oil takes time. No matter how deep you pull the vacuum, no matter how big your pump is, no matter how big your hoses are. It takes time. So if you're a service tech and you put in a new evaporator coil and you're trying to pull a vacuum on the whole system, for example, compressor, everything, lines, it's going to take a while. It just is. No matter if you use big hoses, big pump, it's just going to take a while. It's not going to take as long if you do it my way, but it still might take a couple hours in some cases.
What product is you put nitrogen, a little bit of nitrogen for a little bit, and then do a vacuum?
Okay, so common, that's called triple evacuation. That's the term that they use for it. Common misunderstanding is that nitrogen absorbs the moisture, and it doesn't. Nitrogen does not absorb moisture. But it can displace it, and you can add, and so that's that whole idea of purging first. I don't just put nitrogen in and let it sit. I blast it through. So if you have a system where you're doing service on it, and it had refrigerant in it before, and it had oil in it before you pull a vacuum, blast nitrogen through it, and that will speed up your vacuum because it's the energy that you're adding. It helps stir up the oil, it helps create turbulence, and that gets the moisture out.
Back in the days when, well, before we started using nitrogen, we used to use R12 liquid R12. That was that burn out any liquid.
Yep.
And it was really efficient.
Yeah, R12, R11. I mean, R11 was amazing at that. Yeah, sure. Anything that's, because what you're doing is you're adding, and again, if you're doing liquid, you have a lot more density. It's a much more dense fluid, and so it'll blast everything out of there. Nowadays, when we're using gases, it's not quite as effective, but still, it's always more effective to force it through with energy than it is to just put it in and let it out, right? Letting it out's fine, and even doing a proper nitrogen pressure test, that can help. But I always, before I start brazing and through that whole process, I'm always, blasting a good amount of nitrogen through, and that will help with that. Because again, that refrigerant molecule gets entrained when it was under pressure, when it was operating. It gets entrained in that oil, and it does take a little bit of energy to get that disconnected from that oil. It actually has bonds.
Quick question.
Throw it in my hair.
Yeah.
All right, for example, say you're a vacuum system, like a condenser, the lines and everything. And does the vacuum can withdraw the oil out of the compressor?
No, it's not going to. So the only way, again, a vacuum pump can only pull, the only way that it could ever pull a liquid like that is if it was drawing on a line that was completely filled with it, right? So if you had your suction line was completely full of liquid, it could suck it in and then that would damage it. But then at that point you have other problems, right? Like you're never going to have, but it's not going to pull it out of the compressor. Because again, imagine the oil is sitting in the bottom of your compressor, and your compressor is an open shell. It's just a shell. It has the compression chamber in the top, and it's all sitting in there. There's no way it can pull it up. It would have to boil it first. And if oil in a refrigeration system was going to boil, that would cause all kinds of other problems. You have to get down to like next to a perfect vacuum. So in that sort of like 1 micron sub range for it to actually start to off-gas oil. And we did all kinds, because there was a bunch of guys who were saying that a while ago, and we did a bunch of research with the oil manufacturers and all that. You are not evaporating oil out of the system. You are releasing, because so sometimes, if you look at a compressor that has a sight glass in it, which there aren't many in residential, but in commercial, if you're pulling a deep vacuum, you'll watch bubbles going up through the oil. But that's just refrigerant and moisture that are making its way out of, in the sight glass. That's not the oil boiling. The oil is not boiling. Yeah. And you can know that because we've done the test. You take refrigerant oil, you take vacuum pump oil, whatever, and you put it into a glass container and you pull a vacuum right on that container and it doesn't boil. It just sits there.
It sounds like you're about to get to it when we come back, but it sounds like the time it takes to set up your nitrogen is probably a lot less than it takes waiting for that vacuum to finish.
Correct.
Without it.
Absolutely. Nitrogen is for purging, flowing, pressurization, all that. It's really useful. It saves you a lot of time. And again, a lot of guys will say, well, I don't care how long the vacuum takes because we're waiting on other things. I'm wiring stuff up while I'm doing that. But again, remember, deep vacuum is the 4th leak detection proof, right? So if you get to do leak detection, you get to do vacuum, and you get down to that deep vacuum, and you can see it hold, then you know you're good. If it takes you a long time to get down to that deep vacuum, it takes you 3-4 hours, and now you get to the end and it isn't holding vacuum, and you're ready to leave the job, that's a real problem, right? So getting it down in 20 minutes, so you know within 20 minutes that it's deep and it's holding, now you can release charge with confidence. You know you're going to get out of that job on time. So it isn't just getting it done fast because you have other things, because it is getting in the way. It's getting it done fast so that you're confident when you're ready to fire that thing up, that you don't have leaks. It's that final test. Which again is another way to, that's why you don't have to spend as much time on the pressure test, because you're hitting all these points, because you did a visual, you did bubbles, you did pressure, you did vacuum, decay test. And those all have different benefits, but when you stack them together, they also have the benefit of knowing that you have a clean, dry, tight system, which is big.
So one point is also the vacuum pump oil that will affect, if they contaminate, that will affect the system?
Yes. Will it affect the system? No, it will just affect the ability to pull a deep vacuum. Now again, this is where, to your point, this is one of the things I'm going to harp on in the next thing. Is your vacuum pump working? Right? Take a micron gauge, hook it right to the vacuum pump, turn it on. It should pull down below 50 microns in like 30 to 60 seconds. If it doesn't, your vacuum pump's not working right. And it's usually oil. And sometimes it takes multiple oil changes to get it all cleared out. Vacuum pumps, if you've ever run a vacuum pump with contaminated oil in it, like really dirty oil, like where you had a wet system and it got all, watch how hot that pump gets. Like it gets, I mean, that thing will just, you will smoke that pump in no time. It's really bad for the pump to run dirty oil in it, which is why you should have a pre-check test before you pull a vacuum. And do you have to do it every day? No. Do it once a week, do it whatever. But just hook the micron gauge to it, see if it pulls down to under 50 like that. If it doesn't, change the oil.
How often to change it? Bucket multiple.
Again, back in the day, they used to say, at every use, change the vacuum pump. Well, whatever. Nobody changes it at every use. But if you're testing it regularly, so you're doing a visual test, and you know that last time in 30 seconds it pulled down to 50, and this time it took it 2 minutes, change the pump oil. That's where it's the advantage of knowing your tool. You know what it can do, because you got an older pump, maybe it only pulls down to 50, you know, in 2.5 minutes, whatever. Okay, you gotta, and I always use 50, because if it doesn't pull down to 50, I'm not even using that pump. Modern pumps should pull down to 50 or below. If you're pulling, if it's only getting down to 200, I wouldn't use that pump. It's gonna be a pain in your butt. It's gonna take longer every time. All your modern pumps, your JBs, your Navacs, your Field Pieces, your Robin Airs, your Yellow Jackets, all the good two-stage modern pumps will pull down to below 50 like that.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.